In the last lesson we talked about superposition, and that's where waves interact with one another in a medium when they end up in the same position. So we talked about constructive superposition, when you had two waves on the same side of a medium reach the same position and add together, making a larger amplitude wave. And we also talked about destructive superposition, where you had waves on opposite sides of the medium, and when they reach the same position, they destroy one another. They subtract the amplitudes. Now we're going to look at this one more time, but in a periodic wave. So it's going to continue making waves. So notice how they're traveling to the right, but something odd happens now. Because we've got reflections coming off the C-clamp side of the wave, now you can't really tell what the original waves were doing anymore. You can't really see the traveling part of it anymore. It's just a mess of interference. So we're going to restart this thing, but I'm going to change the frequency. So there are specific frequencies in certain mediums that produce a certain waveform called a standing wave. So we just saw that when you get this interference pattern happening, you can't necessarily see waves traveling anymore. Now it just looks like the particles are moving back and forth in kind of random ways. But we can get rid of that randomness a little bit by choosing certain frequencies. So let's take a look at this. We see the waves traveling toward the C-clamp, and then reflecting on the opposite side, but now there's this interference going on and we can't tell what the original traveling was doing. But look what's happening. These certain pieces are getting just enormous amplitudes. And then other pieces, look at this one right over here, it's just standing still. Now I can't make this frequency quite right. It doesn't work perfectly here, but if I could choose exactly the right frequency, you would see these three positions not moving whatsoever, and then these four positions, 1, 2, 3, 4, just maximum amplitude over and over again, just switching back and forth. And so this is what we call a standing wave. A traveling wave is one where you can actually see them moving back and forth from left to right or from right to left. A standing wave is one where it doesn't seem to be traveling at all. It seems to just be flipping back and forth to opposite sides of the medium. So a standing wave is produced when you get a perfect frequency called a natural frequency. Now let's look a little bit more closely at exactly what's happening when standing waves are produced. So they're the result of interference between two periodic waves. So periodic waves are waves that repeat. Versus, the opposite would be pulses. So a single pulse is what we used in our lab. You just sent one pulse on one side of the wave. It's not a full wave, which is an up and down. A periodic wave is continuous up and downs and up and downs. So they're also called continuous waves. So they have to be periodic waves, and they have to be identical. So that means that they have equal amplitude and wavelength. Those are the two characteristics of the waves that make them the same. Equal amplitude and wavelength. So let's look down here. We've sent two waves toward one another. They're both periodic waves. They have equal amplitude, equal wavelength. I've added this dotted bit on the end just to show that it continues. Okay, so it keeps going up and down and up and down and up and down. So it's not just these two full waves that are interacting with one another. It's a periodic wave that continues. Okay, now when these waves reach the middle, they make this pattern that looks like this. You get a large loop on the bottom, a large loop on the top, a large loop on the bottom, and then it just continues like that. Okay, now we're going to label some of these parts so that we can talk about them a little bit better. So these parts here, this one, and this one, and this one, we can call them loops. The more specific, the more technical word is an antinode. Now I started with antinode because these loops are the most obvious part of the waveform, but there's also these parts in the middle over here, here, here. These, if these are antinodes, these are called nodes. Okay, so a node is where the waveform doesn't seem to move at all. It just holds still. So if we looked at just this particle on the medium, that particle would not be moving anywhere. It would just be standing still. And that's because no matter where you are on the wave, you're getting opposite pieces. So you'd be getting a loop on this side from, say, the wave moving to the right, and you'd be getting a loop on the other side from the wave moving to the left. And so they're always going to cancel out no matter which part of the wave you're looking at. The antinodes, though, they flip back and forth over and over again. So we've got antinodes, which are the loops, and nodes, which are the points that don't move. The antinodes are the parts that are constantly experiencing constructive superposition, and the nodes are the parts that are experiencing destructive superposition. So a standing wave is a waveform that is caused by traveling waves interacting with reflected waves, causing this wave pattern that doesn't seem to be traveling anywhere. It's just got nodes and antinodes, spots that are not moving, and spots that have maximum amplitude. And so resonance is a type of standing wave that is caused by that same thing, except because you're adding energy to it on one side constantly, and the reflections are adding together with the original traveling waves, you get growing and growing amplitude. Okay, so let me write that another way. Resonance is caused by waves interfering with one another, causing their amplitude to continually grow. Let's take a look at our example from before again. Energy is being put into the string on the left, and that energy is reflecting back when it reaches the C-clamp. And so that energy is adding together in a certain frequency, causing these large antinodes and nodes. And notice how the amplitude is just growing continuously. That only happens at certain frequencies. Let me give you another example that you might relate to a little bit more easily. Hopefully it's from your experience a little bit. So this is an electric guitar. It has no resonance chamber. Uses the word resonance. So it's just a solid piece of wood. It has some cutouts for electronics and things like that, but it's basically a set of taut strings stretched over some electronic pickups. So when I play a chord, you can hear it. It's not necessarily very loud, which is why you're supposed to plug an amplifier into that pickup over there. But if instead I use this guitar has a resonance chamber. That's its sound hole right over there. So if I play the same chord with this guitar, it's a lot louder. It rings out a lot more, and that's called resonance. So what's happening here is that each string is vibrating with a certain frequency. And when that string vibrates, it is also transferring that vibration to this piece over here. This piece is where the strings connect to the body of the guitar. And when this piece starts vibrating, it vibrates this top piece of the guitar body with that same frequency. And when that top piece of the guitar body starts vibrating at the same frequency, so does the air inside the chamber. And so you get that same frequency vibration coming from the chamber of the guitar body, and it's called resonance. So that little vibration from the guitar string becomes a much bigger vibration from the air inside the guitar. Any frequency that causes that growing amplitude in a certain medium is called a natural frequency. Okay, so it's a frequency that causes a standing wave. So, for instance, my acoustic guitar, if you play a B note, it will sound louder than any other note that you play on the guitar. Or, if you are sitting beside that guitar and nobody's playing it, but you hum a B note, then my guitar will start humming along with you. It's really strange. Sometimes you'll be sitting there and maybe, I don't know, I'll be making a sound for my kids or something like that, and then I'll start hearing some other humming in the background, and I'll realize that it's my guitar humming back at me. Another thing that you can do is go into your shower, and you might notice that if you happen to sing in the shower, there are certain notes that you sing that just sound louder than all of the rest of them. Your shower will have a certain resonant frequency. Now, we call that a natural frequency because that's going to happen at multiple frequencies. So there's not just one specific note that makes your shower hum back at you or lets the amplitude grow a lot. There are going to be multiple natural frequencies or multiple harmonic frequencies. Let's look a little bit more closely at the properties of harmonics. So first of all, we need to recognize the parts of a standing wave. We looked at this before, but let's say we're going up, down, and back to the middle again. So remember that this is one cycle of a wave. Okay, we can call this one wavelength. That lambda, here let me spell that for you, L-A-M-B-D-A. That's the Greek letter lambda. That's the symbol for one wavelength. Okay, so one cycle means it goes up, down, and up again. Has a crest, a trough, and back to neutral. Okay, one wavelength has two loops, or two antinodes. I will alternate between calling them loops and antinodes, so just so you can keep track. One loop, that means, or one antinode, is half a wavelength. Okay, that's going to be important for when we're counting parts of harmonics. Okay, so if you're looking from here to here, that's half a wavelength, right? It has one crest, but it hasn't gotten to the trough yet. And so that would be half a wavelength. That's one antinode. So a half a full wave, half a wave, has an antinode and two nodes. Okay? Now, the fundamental frequency of a medium is the lowest frequency that produces a standing wave. Okay? Or the lowest natural frequency or the lowest harmonic frequency. Those all mean the same thing. So it would look like this. You can have a standing wave just like that. Think about if you were using a skipping rope and you and a friend were just waving it back and forth like this. Technically that would be a standing wave, right? You are making waves on that medium, but they don't seem to be traveling back and forth. It's just you're making an antinode, and that's it. And you two holding that wave, those are the two nodes. And so that would be the lowest natural frequency for any medium. One antinode. This is the fundamental frequency. So up here, this is the antinode. And over here, and over here, those are the nodes. So, the fundamental frequency of any medium has one antinode and two nodes. Okay? Now I can show you this with the guitar as well. So a guitar string is attached to the guitar in two places. It's attached way up here on the neck, and it's attached way down here. Those are the two places it's attached. So those would be the two nodes of this fundamental frequency. Now if I pluck this string right in the middle, you can't really see the vibrations because it is so fast, but what's happening is this string is just moving back and forth exactly like this. Okay? It's moving with one antinode. It's just wiggling back and forth so quickly that you can't see it. So this is called F0 or F0, which is the first harmonic or the fundamental frequency. Same thing. It's the lowest frequency that causes a standing wave in some particular medium. It's going to be different for every medium, but in any particular medium that you're talking about, it's going to have a fundamental frequency. Now we just said that a medium is going to have one fundamental frequency, the lowest frequency that's going to cause a standing wave, but it's going to have multiple harmonics, which means that there are multiple frequencies that are going to cause a standing wave to be produced in a certain medium. So with a guitar, if I just play an open note like that, I'm making one antinode, and there are two nodes, one on the neck side and one on the body side. Okay? But I can produce another node. I can artificially put one right in the middle, right over here. So if I just touch my finger down to this string and then pluck it, notice what happens. So this was the open note. That's the fundamental frequency of my top string. And then if I put down my finger on the 12th fret, I'm putting another node there, which is essentially cutting the string in half. It's producing one antinode over here on this side and another antinode over here on this side. So now my string has two antinodes and three nodes. So that's one full wavelength, and it has increased the frequency. It has doubled it. Okay? And with music, when you increase the frequency, you hear a higher pitch. Okay? And that's why it starts fundamental like this. And then when I add a node in the middle, it's twice as high. Okay? Now, if I would triple the fundamental frequency, so I just doubled the fundamental frequency like this, by doing that, I can slide my finger even farther up here, and I can find the position that would cause three antinodes. And that would be the third harmonic. Okay, see if I can find it. There it is. And as you try and do that more and more, it's more difficult to figure out where it is, and it's more difficult to get it to ring out properly. So fundamental, first harmonic, second harmonic, there you go. Okay, so as you move up the frequencies, you get higher and higher harmonics. So let's draw a picture of this here. If I triple the fundamental frequency, let's say that F0 was 100. 100 hertz. If I triple the fundamental frequency, I'm going to get 300 hertz, right? So if I double it, that would be F1. That's 200 hertz. And if I triple it, I'm going to get F2, which is 300 hertz. Now we can draw a picture of that. So F0, or the fundamental frequency, looks like this. It's just one antinode that flips back and forth. If I double that, instead of having one antinode, now I'm going to have two antinodes. So it looks like this. A full wave. Now, if I triple my fundamental, that means now I'm going to have three antinodes. And so it will look something like this. That would be the third harmonic, triple the fundamental frequency. Now, we can also call these overtones. Okay, so the fundamental frequency is not an overtone. It's the first harmonic, though. An overtone is any natural frequency above the fundamental frequency. So this one would be called the first overtone. And this one would be called the second overtone. Now, it's not really important that you be able to count it both ways, but it's not a bad thing to understand. When someone's talking about an overtone, they're talking about the same thing as a harmonic, it's just it's counted differently. Okay, so F0 is harmonic 1. I'm just going to write H1, but it's not an overtone. The first overtone is the second harmonic. It's H2. And then the second overtone is the third harmonic, H3. So the harmonic number is just one above the overtone. They're exactly the same thing, they're just counted starting at different places. So quickly, if you would quadruple the fundamental frequency, so if you started off with F0 is 100 Hertz again, then if we just move on down to quadruple that, so that would be F3, okay, you're not quadrupling this number down here, because that wouldn't make any sense, right? No matter what you would be doing, if you're starting with 0, it doesn't mean anything to quadruple it, right? You'd still have 0. But rather, you're counting up. So we're going to F3 then. F3 would be quadruple F0, right? F0 is the fundamental, F1 is double that, F2 is triple the fundamental, and F3 is quadruple the fundamental. And so this would be 400 Hertz. You do quadruple the frequency. Okay, and we already drew what that would look like over here. 400 Hertz now, or the fourth harmonic, is going to have 4 antinodes. So like this. 2, 3, 4. Okay, now if it was a guitar string, it wouldn't look anything like this, right? Because a guitar string is really taut and flat, like this, and how much it deviates from flat when you pluck it is oh so little. And so it's not going to look like this when you find the fourth harmonic on a guitar string. It's going to look barely different than flat like this, and especially because it's moving so fast you can't really see it. Now here you see some reminders of what we just talked about. Feel free to check the notes for that stuff. What I want to do is do this example over here. So we're told that the fundamental frequency of a certain medium is 200 Hertz. Okay, and we're supposed to find the sixth harmonic frequency. So, going through the list, F0 would be the first harmonic frequency. So let's count this out. F1 would be the second, F2, F3, F4, F5 would be the sixth harmonic frequency. Okay, so F5 would be the sixth harmonic frequency, and so we're supposed to figure out what's the frequency of that wave. Okay, so this is 200 Hertz. And to figure out what the sixth harmonic frequency is, we just take this guy and multiply it by 6. That's it. Doing math with harmonics is pretty simple. So we want to multiply this by 6 to get us to the sixth harmonic frequency, which gives us 1200 Hertz. Now, if it asked you, find the frequency of the fifth harmonic of the fifth overtone, then you'd have to translate that in your mind. What does the fifth overtone mean as far as harmonic frequencies go? So the fundamental is 0, it's overtone 0, and then as you count up, that's giving you the overtone number. Okay, so this number here, beside the frequency, that tells you what overtone it is as well. So this would be harmonic 1, but it's overtone 0, which isn't really an overtone. This is harmonic 6, overtone 5. And now our last example. A guitar string has a length of 0.9 meters and a fundamental frequency of 250 Hz. The string is vibrating with its frequency equal to the third harmonic. What is the frequency of this vibration? So, if the fundamental is 250 Hz, and we want the third harmonic, we're just going to multiply this by 3. The first harmonic is 1 times the fundamental, because it is the fundamental. The second harmonic is 2 times, the third harmonic is 3 times. And so this gives us a frequency of 750 Hertz. What is the wavelength of this vibration? Okay, so we need to draw this out in order to figure this out. So the third harmonic has 3 antinodes, right? So here's 1 antinode, 2 antinodes, 3 antinodes. Okay, so it has 1, 2, 3, 4 nodes, and 3 antinodes. Okay, this guy up here is an antinode. Okay, so the wavelength of this vibration has 2 loops, right? We remember that a wavelength has a crest and a trough. It's got to have both. So the wavelength is right here. This would be the wavelength. Okay, so we can think of this in a number of ways. We can decide, using my total length of 0.9 meters, that's this whole distance, what fraction of that 0.9 meters will give me 1 wavelength. So we can use fractions to figure it out. We can also figure out what is the length of 1 antinode, and then just multiply it by the total number of antinodes that I need. So for 1 wavelength, I need 2 antinodes. So the 2 ways that we can do this are like this. The full length of this string is 0.9 meters. Now for 1 wavelength, I need 2/3 of this string, right? Because I need 2 antinodes, and there are a total of 3 antinodes on this string, and so I need 2/3 of that. So 0.9 meters times 2/3 gives me 0.6. 0.6 meters would be the wavelength of this particular vibration. Okay, so 0.6 meters, that's the wavelength. You could also figure out what's the length of 1 antinode and then multiply it by 2, right? So then I would take my full string length, which is 0.9 meters, and I can divide it by 3 to get me the length of 1 antinode, 0.3 meters, and then I can multiply that by 2. And that would get me the wavelength. So that's 0.6 meters. That would get me the full wavelength. Now the last piece, this is going to bring us back to a previous section. What is the speed of this wave, or how fast does it travel along the string? Okay, so if I were to pluck the string on one end, how long does it take that vibration to reach the other end of the string? So we have only one equation for speed of a wave. Speed equals frequency times wavelength. Okay, we could have also done wavelength divided by period, but we have nothing in this question that talks about period. And so we're just going to go speed equals the frequency of the third harmonic was 750 hertz. And the wavelength of that harmonic was 0.6 meters. And when you put that together, you get 450 meters per second, which is crazy fast, but try to imagine how fast a wave would move from one end of a guitar string to the other. You can't even see how quickly it's vibrating back and forth, and so it really is that fast.